Okay, so I'm going to be working on number 13 here. The population of India was about 1.41 billion people in 2021, and at that time was growing at a rate of 8.7% per year. Write a formula for the population P of India in billions as a function of T years since 2021. So it tells us here that we have this population here, and that our starting year is 2021, and we're saying that we're T years since 2021. So what that means is that our initial population was 1.41. So we get to say that population equals 1.41. And then we're going to multiply by our rate. So because we're increasing at 8.7% as a decimal, that's going to be 1.087. And then we raise this to the t power. So now for part B, if the growth rate stays constant, predict the population of India in the year 2024, round to 2 decimal places. So 2024, notice our formula started at 2021. So that's 3 years after where we started. So we're going to say that P of 3 is going to be equal to 1.41 times 1.087 to the 3, which is just equal to 1.81 billion. Okay. Then for C, by what percent did the population of India increase in the 2-year period between 2021 and 2023? So for this one, we need to figure out the population in 2023. So that's 2 years after 2021. So P of 2 equals 1.41 times 1.087 to the second power. So if we enter this into our calculator, we should get that P of 2 equals 1.66. So then to find the percent increase, we can do 1.66 over our initial 1.41. So if we do that, we get 1.1773. But if we do it with the full, before we do any rounding at all, this should come out to be 1.1816. So then because we're saying that what percent did the population increase, really we're concerned with these numbers here. And then that's as a decimal, so to make it a percent, we multiply by 100. So we say that we increased by 18.16%. Okay, number 14, an investment decreases in value by 5.3% each year for 3 years. By what percentage does the investment decrease over a 3-year period? Round your percentage to decimals. Okay, so we need to figure out kind of like what we put in for like this part here. So we're gonna have 1 minus r here because we're decreasing. So if you're increasing, you can do 1 plus r. Since we're decreasing, it'll just be 1 minus r. So you want to figure out what this number here is going to be. So we have 1 minus 0.053, which is going to be 0.947. So we know that each year we multiply by 0.947 to get our new amount. So if we take this and we multiply it to the 3rd power, what we're going to get is 0.849278. So then if we want to find the amount that we decreased, we just go from basically 100% to this percent. And we find that we can do 1 minus 0.849278, which is just going to be 0.15072, or so that we decreased by 15.07%. Okay, so number 15, we're going to be doing some like kind of graph analysis. So we're saying that these equations can all be written in a general form, y equals a b to the t. Then we say which function has the largest a value. So the way that we can think about this is we can look at what happens whenever t equals 0. So if t equals 0, we should have y equals a, because b to the 0 is going to be 1. So you get just y equals a times 1. So if we look at the 0, or whenever t is 0, we can look at which point is the highest. We can see that right here on b, this point here is the highest. So that means that b is going to have the largest a value. Then for which functions have the same a value, so we do a similar thing where we look at their intercept here. You can see that these two both intersect at that same point there. So we know that a and c have the same a value because they have the same y-intercept. So a, and then c. So which functions has a b value between 0 and 1? So if you're between 0 and 1, that means your graph is going to be decreasing, or you're going to be looking at some sort of decay. So the ones that have that is something like b, because we're decreasing, and a, because we're decreasing. So part C, it's going to be a, and then b. And then which functions has a b value greater than 1, I can explain. So these are ones that are increasing, so that's going to be c or d, because if b is greater than 1, you're going to start getting like really big numbers as you go out towards t getting bigger. So we say that c and d has a b greater than 1, and again, that's just because they're increasing. Okay, so for number 16, we're given a sample of rock was found to contain a mixture of minerals, part of which were radioactive and decreasing over time due to radioactive decay. The mass m of the rock in grams after t years is given by this function here. So what is the equation of the horizontal asymptote? So sketch a graph to help with this. So if we start kind of just plugging in numbers, we can see that at t equals 0, we're going to have 15 plus 3.8. So at t equals 0, we should be like somewhere around here. And then as we keep plugging in larger and larger values for t, we're going to see that this term here is going to get really, really small, because it's kind of like taking two fractions or two decimals and multiplying them, which makes it smaller. And then we're going to have this number times a really, really small number. So it's kind of like this will slowly become negligible, which means that we'll kind of approach this 15 here. So that 15 is our horizontal asymptote. So I'm going to kind of draw a dotted line here. So we should expect that as t becomes really big, that we're just going to kind of approach that line. So maybe we get something kind of like this here, or something kind of like that. Sorry. Okay. So what is the equation of this horizontal asymptote? It's just at m equals 15, basically. So what was the initial mass of the rock? Include units. So this is where we plug in t equals 0, right? So if we plug in t equals 0, we get 15 plus 3.8 times 1. So that means that we're going to have 15 plus 3.8. So the initial mass is equal to 18.8. And our units here, it tells us, is in grams. So grams. And what should the mass of the rock eventually approach as time approaches infinity? Explain using units. So if we look at up here, we said that we have this horizontal asymptote. We know that as time goes towards infinity, that kind of what we were talking about in part A, that this is going to approach 0, and then we'll just have 15 left. So eventually, the mass of the rock will just be 15 grams. Again, that's because as t goes towards infinity, the mass will just approach the 15 because this part here will be 0. Okay, for number 17, we're going to be working on some transformations. So we're given this exponential function, f of x equals 2 to the x, and then we're going to write a function for one that's reflected across the y-axis. So if we reflect it across the y-axis, what we change is we put a negative inside of this part here where our x is. So the reflection reflection is going to give us 2 to the negative x. And then we're told that we're stretched vertically by a factor of 3 and shifted 1 unit up. So if we take this and we stretch it vertically by a factor of 3, we just put 3 times it out front. So we have 3 times 2 to the negative x. And then we shift it 1 up. So all we do is just add 1 to the outside. So what we end up with is this equation here. So we say that f of x equals 3 times 2 to the negative x plus 1. Okay, and now for part B, we're given a function that reflects across the x-axis, compressed horizontally by a factor of 1/3, and shifted right 1 unit. So first we can start with the reflection. So if we reflect it across the x-axis, that's going to be like taking it from up here and bringing it down here like that. So to do that, all we have to do is put a negative out front. And then next, we're told we compress it horizontally by a factor of 1/3. So whenever we're adjusting things horizontally, we have to look at where we adjust kind of our x up here. So if we're compressed horizontally by a factor of 3, that means that we're actually going to be multiplying by the reciprocal of that, which is just going to be 3. And it seems kind of counterintuitive, but if you go ahead and just plot a bunch of points, you'll see that you have to multiply by that reciprocal in order to get it to work. So for horizontal compression, you're going to be multiplying it by 3. So this correlates to a horizontal compression of 1/3. Then the last thing it tells us is that we shift it right 1 unit. So again, we're looking horizontally, which means we'll be kind of adjusting things that are relating to this x outside or inside. So from here, we're just going to take this, and if we shift it right, we have to do +1, and we include this with our 3 here. So it's going to be x minus 1, just like that. So our second function here is going to be -2 to the 3x minus 1, just like that. Okay, so for number 18, we have a population of ants in a colony growing at a continuous rate of 6.2% per month. The initial population of the ants was 200,000. Write a formula for the population P of the colony at t months. So notice it tells us here that it's continuous. So if it's continuous, that's whenever we have our Euler's number, which is E, included in our formula. So we're going to have that our population P is going to equal our initial population, which is 200,000, and then E to our continuous rate. So our continuous rate was 6.2%. So we just make that as a decimal. So 0.062. And then we have our T right there attached to our rate. Oops. So that's our formula here. So now, what is the monthly percentage growth rate? So this is different because here we have our continuous rate. So what we're doing is we're kind of taking this formula that we're given here, and we want it to be sort of in this formula here. So whenever we solve for this, we can kind of immediately just divide out our initial populations on both sides, and then we just get that e to the RT is going to equal, this is going to be K, is what we denote our continuous rate as a lot of the times. So I'm just going to use K here. So this is going to be equal to R to some power T. So from here, we want to solve for this R here. So we can just take everything to the root T power, basically. And another way to think about this is you're just taking everything to the exponent of 1/T. And if you do this, you get that R is going to equal E to your continuous rate. So if we just plug this in here, we get that R is equal to E to 0.062. And then if we plug this into our calculator, we get that our percentage growth rate for per month is 6.40%. Okay, so number 19, fill in the blank. If f of t equals this function, then if t increases by 1 unit, the function should decrease by so much percent. So we see that we have this number here is less than 1, which means that we're decaying, or whenever we plugged it into our formula, we had something like 1 minus r to the t with our initial amount. So here, because we have 1 minus r, let's say 1 minus r equals 0.649. So then if we solve for r here, we get that r is going to equal 0.351, which means that every time we increase t by 1 unit, our function f should decrease 35.1%. So that means here, we're going to say that this decreases by 35.1%. So then for 20 here, fill in the blank. If f of t equals 80e to the negative 0.4t, where t is time in years, then the continuous decay rate is, so because we have this e to some number, this number here is our continuous decay rate, that negative 0.4. And then because we're saying that we're decaying, we kind of ignore that negative sign, or that negative sign is what suggests that we're decaying. So we say that our decay rate is just going to be 40%. Oops, let me rewrite that. So fill in the blank for 21. We have, if f of t equals 80e to the negative 0.4t, where t is time in years, then there will be a decrease of so much per year. So here we have kind of a similar thing that we had on 18, part B, where we're given sort of this form here, that we have some initial amount, e to the kt equals some initial amount, whatever our rate ends up being to the t. So we kind of want to solve for this here. So if we do that, we can divide out our sort of starting amount, and we get e to the kt equals that r to the t. And now we go ahead and we want to solve for r. So to do that, we just take everything to the 1 over t power. And this means that r is going to equal e to the k, basically. So k is negative 0.4. So if we plug this in, we get that r here is going to equal 0.67032. So this isn't quite our rate that we're decreasing by percent-wise. So what we want to do from here is actually solve for, like, in this form here. So because we're saying that we're decreasing because this is less than 1, we want to figure out that percent that we are away from 1. So we know this is going to be equal to 0.67032. Then if we solve for r here, we get that r is going to equal 0.32968. So what this means is that we're decreasing by 32.968% per year. So the question here, then there will be a decrease of 32.97% each year. So then 22, we have true or false. If a population increases by 10% in 1 year, then it will increase by 20% in 2 years. So this one here, the way that we can kind of check this is by setting up our formula where we have our sort of initial amount to our percent that we're increasing by to the t. So then we can just see what happens if we say that we plug in t equals 2. We get that we have so if we plug this in, we'll end up seeing that the amount that we actually are going to increase by is going to be around 21%, because we'll have this 1.10 squared, which is going to be 1.21, which means that we're increasing by 21%. So this one here, 22, is going to be false. Okay, 23, a 5-year certificate of deposit is opened with a $6,000 initial deposit at an annual percentage rate of 2.9%, and it's compounded monthly. So the important thing to notice here is we're saying the annual percentage rate is 2.9, but we're compounding it monthly. So the way that we're going to set up our equation here, we can go ahead and say that our amount is going to equal our initial amount, which is 6,000, times, and then inside of here, because we're increasing, it's going to be 1 plus. Then we're going to have our rate, which is 0.029, and then we divide it by how many periods there is per year. So because this is our annual rate up here, and we want it as a monthly, compounded monthly, we take this and we divide this by 12. So that way, this is now our monthly rate. So then we just have this to the power of t. So here we're wondering how much money will be here after 5 years. So we're saying we're evaluating this after 5 years, which is going to be 12 months per year. And we have 5 years. So that's actually going to be 60 there. It's going to be equal to 6,000 times 1 plus 0.029 over 12 to the 60th power. And then from here, if we plug this in, we get that our amount after 60 months is going to be equal to 6,935.02. And then for part B, what does the percentage, by what percentage does the account grow in 1 year? Round this percent to 2 decimal places. So let's just look at what happens if we plug that in here. 0.29 over 12. So because this is our monthly amount, we have to say that t equals 12 because there's 12 months in a year. So if we plug this in, we'll see that the amount that we multiply it by is going to be 1.294. So the amount that it increases is this here. Or excuse me, this is going to be 1.0294. So this is the amount that it increases here. So by what percent does this grow? That is 2.94%. Okay, starting with 24a, we're going to simplify these expressions completely. So for part A, we have 3 log of x plus 2 log of y. So if it never gives you a log base, what that means is that you assume that's log base 10. So if we start working on this, first thing we see is that we can bring these exponents inside of here. So this is going to be 10 to the log of x cubed plus log y squared. So now if we have 2 logs that are added, we can say that that's log of x cubed times y squared. And then from here, the last thing to do is to recognize that if we have 10 to the log base 10, they sort of cancel each other out, and all that we'll be left with is this part right here, which is x cubed y squared. So now for part B, we have e to the natural log of square root x minus 5 natural log x. So what we can do is start by, first thing is that square root x is the same thing as x to the 1/2. So we can really rewrite this, and then we can also bring this up here. So we can write this as e to the natural log of x to the 1/2 minus natural log x to the 5th. So if we have two logs that are subtracting, we can take the parts that are inside and divide them. So we can say that this is e to the natural log x to the 1/2 divided by x to the 5th. So then, just like with 10 to the power of log base 10, e to some natural log here, they cancel each other out, and we'll be left with x to the 1/2 over x to the 5th. So this is just going to be equal to 1 over x to the 9/2. And where that comes from is if we have 1 over x to the 5th, this is the same thing as x to the negative 5th. Then if we take this x to the negative 5th times x to the 1/2, we add these, we get that x to the negative x to the negative 9 over 2. And then we bring that back into the denominator. So we see that this is going to be 1 over x to the 9/2. 25. The two most intense earthquakes in the world were recorded just 4 years apart. A magnitude 9.5 earthquake hit Chile in 1960, and a 9.2 magnitude earthquake hit Alaska in 1964. How many times as intense was Chile's quake compared to the Alaska quake? Round to 3 decimals. So if we look right here, we're given kind of a formula that we can use. And whenever we say that something is like a magnitude 9.5, we're kind of looking at it on a logarithmic scale, which means that a magnitude 9 is 10 times more intense than a magnitude 8. So if we look at this ratio here for the intensity 1 over intensity 2, so that's going to be Chile's over Alaska's quake, we get that our ratio of our intensities for Chile and Alaska is going to be 10 to our magnitudes. So the magnitude, we'll have magnitude of Chile minus the magnitude of Alaska. So that means that we're going to have 10 to the 9.5 minus 9.2, which is going to be equal to 10 to the 0.3. Then if we plug this in, we see that it's equal to 1.995. So what this means is that Chile's intensity for that earthquake was 1.995 times as intense. Okay, looking at number 26. The graph of y equals log base 4 of x is shown. Let f of x equal negative log base 4 of x plus 2. So why don't we actually just start by kind of drawing a rough graph of this. So we can see that we've reflected it over the x-axis from this negative, and then we've shifted it left to from this. So what this is going to look like is we'll have something kind of like this. And then it's going to be going downwards, kind of like that. So if we look at what are the domain and ranges of this, we can see that, well, our domain, we can see that we never are defined at x equals -2, because we'll have log of 0, which is undefined. So that means that our domain starts at 2, and then we go off towards infinity, positive infinity. So our domain is 2 to infinity, and then our range is going to be -infinity to infinity, because there's no like holes or anything like that. So our range is -infinity to positive infinity. So what are the vertical asymptotes for f of x? So for f of x, our vertical asymptote is right here, which aligns with x equals -2. And then fill in the blanks. As x approaches -2 from the right, that's what that little plus here means, is from the right, f of x approaches, so that's like saying that we're going here and we're going up like that. We see that we're going to go towards infinity. And then as x goes towards infinity, what does f of x go to? F of x just points downwards off to -infinity. Okay, 27, we're going to be solving for x and give your answers in exact form. So starting with 27a, we have 8 times 3 to the x equals 4 to the x. So if we want to get x down from there, and you have two different bases here, you can kind of usually start just from taking like the natural log. So if we go ahead and do this, we can go ahead and say natural log of 8 times 3 to the x equals the natural log of 4 to the x. And we can apply some log rules. So you know, if we have two logs, if we have multiplication on the inside of two logs, it's the same thing as saying that they're added, like this. And then if we have these exponents, we can bring them out front. So now we have natural log of 8 plus x natural log of 3 equals x natural log of 4. So natural log in 3 and 4 are really just some numbers. So let's move this x over here so we can get all our x's on the same side. And then here, both of these have an x in common, so we can factor that out. And then divide everything by natural log of 4 minus natural log of 3. You get that x equals natural log of 8 over the natural log of, and if you have two natural logs subtracting, you can just say it's division, 4 over 3. And then if we go ahead and plug this in, we see that we should end up with x equaling 7.23. So again, over here, it wants our answers in exact form, then rounded to 2 decimals. So our exact form is x equals natural log of 8 divided by, natural log of 4 over 3, or x is equal to 7.23. Okay, part B, we have 10 to the 2x plus 5 equals e to the 7x plus 3. So 10 to the 2x plus 5 equaling e to the 7x plus 3. So we have two different bases here. So we can go ahead and take the log of both sides, and let's take it to log base 10. So if we take everything to log base 10, that cancels the 10 on the right, or the left side. Then the left side, or right side, sorry, gosh, we're going to have log of e to the 7x plus 3. And if we have an exponent, we can just take that and bring it out front. So we're going to have 2x plus 5 equaling 7x plus 3 times log of e. And then from here, we want to get all our x's on the same side. So we have 2x minus 7x times log of e. equaling 3 log of e minus 5. So now we factor out an x. So we'll have x times 2 minus 7 log of e equaling 3 log e minus 5. And then we divide it over, and we get that x equals 3 log e minus 5 over 2 minus 7 log e. And then this as a decimal is approximately 3.55. So our exact form is x equals 3 log e minus 5 over 2 minus 7 log e, or x equals 3.55. And you probably could have approached it the other way by taking the natural log, and you should wind up with the same decimal, but your exact form might look a little bit different. But as long as you get the same decimal answer, you know that your exact form should be the same. Okay, so moving on to part C, we have log x minus 3 plus log x plus 3 equaling 2. The first thing we should see is that we have two logs that are added. So it's the same thing as if it was log of x minus 3 times x plus 3 equaling 2. So from here, what we can do is take everything to the 10th power, like this, and we get that x minus 3 times x plus 3 is going to equal 10 to the 2nd power, which is just 100. And then right here, this is a difference of squares. This is going to be x squared minus 9 equaling 100. So x squared equals 109, or x equals plus or minus square root of 109. So if we look at this, this negative version here is extraneous, and if we go ahead and plug in this negative here up here, notice how we'd get log of some negative number, which does not exist. So that means that really our only answer is the positive version. So x equals the square root of 109. So anytime that you solve an equation with logarithms in it, it's really good to go ahead and just take your answer and plug it in and make sure that you get a real answer, because a lot of the times you end up with these extraneous solutions that don't actually exist. And then this is just a decimal, is x is equal to 10.44.